I'll be going over some review material today for Math 2412. You should have an exam coming up soon, so this is some material that you've already seen these past few weeks just to kind of go over and get more of a foundation for any exams coming up on the material. The first thing to review is the unit circle. So here is the full unit circle. Just to kind of briefly go over the unit circle, it has radian and degree measures. So we're going to go over some of the main ones. Right here we have pi over 6. That's the angle in radian measures. That's equivalent to a 30-degree angle in degrees. And that goes with the point on the unit circle of square root of 3 over 2 and 1/2. The next value we see is pi over 4, which is the equivalent to 45 degrees. And the point there is square root of 2 over 2 and square root of 2 over 2. We also have pi over 3, which is equivalent to 60 degrees. And the point right there is 1/2 and square root of 3 over 2. Now you notice that these are the coordinates right here in the first quadrant. The points were all positive. These values are going to repeat throughout the unit circle in different quadrants for corresponding angles. However, the signs change. So notice in quadrant 2, we have the same values except the first coordinate on all of these is negative and the second coordinate is positive. In quadrant 3, you'll see some of the same repeating values for corresponding angles. However, both of the coordinate values on the point are negative. And then in quadrant 4, the first coordinate is positive on all of them, and the second one is negative. It's important, some students, you can create the unit circle yourself. That's a great advantage. So that's what we're going to go over next, is how to construct the unit circle yourself. So the first part, we start here with a circle, unit circle, divided into fourths. Then we're going to cut those in half so that we have an even amount of eight sections on our unit circle. Okay, then we're going to start labeling all of these. We're going to start labeling our radian values. We start here at 0, and then we're at pi over 4, or 1/4 pi, and we're just going to increase by a fourth. So then 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, and then 8/4 pi. Okay, now we're just going to reduce the ones that are reducible. So the ones that reduce, 2 pi over 4, pi over 2, or 1/2 pi. 4 pi over 4, 4 over 4 is 1, so 1 pi. 6 pi over 4, or 6 over 4, reduces to 3 over 2, so 3 over 2 pi. And 8 pi over 4, 8 over 4 reduces to 2 pi. So those are our radian values here for the angles. Now we're going to go through and mark the degree values. We're going by 45 degrees. So we're here at 0. Next is 45. We add another 45, we're at 90. Add another 45, we're at 135. Continuing on, 180, 225, 270, again adding another 45, 315, and ending with 360 for our degree values. Okay, now we're going to go in and put the points that go with all of these angle values that we found, right? So starting here, let's actually start with our first 4 points that we have. So here we're at 1, 0. Okay, remember these make the x and y axis. So if you're on the axis, right here in the center is 0, 0. So if we go over, you're at 1, 0. When you go up, the point is 0, 1 right there. When you go to the left, you're at -1, 0. And then when we go down, we're at 0, -1. Then after that, all the other points are going to be square root of 2 over 2 and square root of 2 over 2 for both x and y. Just remember in the different quadrants, the signs of the different coordinates. So then in quadrant 2, it's negative square root of 2 over 2 and square root of 2 over 2. In quadrant 3, 5 pi over 4 is going to have both coordinates negative, negative square root of 2 over 2 and negative square root of 2 over 2. And in quadrant 4, again, we're looking at, well, maybe I didn't mention it, but we're looking at all the ones with a denominator of 4. They all have square root of 2 over 2 and square root of 2 over 2. But again, the sign, be careful. In quadrant 4 here, the first sign is positive, and the second sign, the sign of the second coordinate, is negative. So this is the first part of constructing the unit circle. And then we're going to go on to now the second part. So again, we start dividing the unit circle into fourths. Okay, but now here we're going to cut it a little bit more, so we're going to end up with 12 equal pieces. Okay, we're going to start by labeling our radian measures. Okay, so we start here at 0, and then we're going to go by sixes, pi over 6 or 1 pi over 6, and then 2 pi over 6, 3, 4, 5, 6 pi over 6, continuing with the pattern, 7 pi over 6, 8, 9, 10, 11, and then we're at 12 pi over 6. So we complete this going by sixes, 1/6 each time. Now, just like before, we need to reduce all the fractions that are reducible. 2 pi over 6 reduces to pi over 3. 3 over 6 reduces to 1/2, so 1/2 pi or pi over 2. 4 pi over 6 is 2 pi over 3. 6 pi over 6 is pi. 8 over 6 reduces to 4/3, so 4/3 pi. 9 over 6 reduces to 3 over 2. 10 over 6 is 5 over 3. And the last one, 12 over 6 is 2, so we get 2 pi. So those are our radian values. Now we're going to go through and write the equivalent degrees. So for this one, we're going to go by 30 degrees each time. We start at 0, we add 30, and then we're just going to keep adding 30 each time. Then we get 60, 90, add 30, we get 120, 150, at pi we're at 180, 210, 240, 270, 300, another 30 is 330, and then you add 30 to that, you're at 360. So doing that gives you the equivalent degrees for all the radian values that we had. Now we're going to go through and write the points, okay? Starting with the ones on the x and y axis. So again, if you can remember the x and y axis that this came from, right here at the center, we're at 0, 0. So if we go out to the right, that point is 1, 0. If we go up, we're at 0, 1. To the left, -1, 0. And then if we go down, we're at 0, 1. And those are actually the same as from part 1. Now to fill in the rest of them, any of these fractions that have a denominator of 6, we're going to have square root of 3 over 2 for the x coordinate, 1 over 2 for the y coordinate. However, just be careful of the sign values they're going to have in each quadrant. So in quadrant 1, all the points are positive coordinates x and y. Quadrant 2, denominator of 6, it's square root of 3 over 2 and 1/2. However, the first coordinate is negative. In quadrant 3, denominator of 6 also has square root of 3 over 2 and 1/2, but both are negative, and that's true of all the points in the third quadrant. They're both negative. And then in quadrant 4, square root of 3 over 2 and -1/2 for the 11 pi over 6. So again, all of the denominators of 6 are going to have square root of 3 over 2 as the x coordinate, 1/2 is the y, just being careful with which the signs are in every quadrant. Now looking at all of our values with a denominator of 3, the point is going to be x coordinate 1/2 or -1/2, and the y coordinate is going to be square root of 3 over 2 or negative square root of 3 over 2, again depending on the quadrant you're in. Quadrant 1 is positive, so we have 1/2 and square root of 3 over 2. In quadrant 2, for 2 pi over 3, again denominator of 3, the first coordinate is negative, -1/2 square root of 3 over 2. In quadrant 3, 4 pi over 3 is negative for both coordinates, -1/2, negative square root of 3 over 2. And the one in quadrant 4 is 5 pi over 3. It's a positive 1/2 and a negative square root of 3 over 2. Okay. So that's, again, the second part of the unit circle, looking at dividing it in radians by sixes or in degrees by 30 degrees and filling in the appropriate point values. Okay, these are all the values we just found. So the last thing we're going to do is bring in all the points from the first part that we did, which were all the multiples of 45 degrees or pi over 4. So let me draw those cuts in here and bring those values in. Okay, remember this was pi over 4. Over here it's 3 pi over 4. Over here was 5 pi over 4, and then over here it's 7 pi over 4. And then let's bring in the equivalent degree values. Here we're at 45. Over here we're at 135. Then we go to 225 and 315. Hopefully you remember what those points were. Square root of 2 over 2 and square root of 2 over 2. So in quadrant 2, the first coordinate is negative. In quadrant 3, both of these coordinates are negative. And in quadrant 4, you have positive for the x coordinate and negative square root of 2 over 2 for the y. So again, a brief review over how to construct the unit circle yourself. And this can really come in handy if you know how to construct the unit circle. You have all these values that you can use as you complete your work for the course. Okay, so let's look at how we're going to be converting degrees to radians. Let's start with formula here. If you have a value given in degrees, you want to convert it to radians, you're going to multiply by pi over 180. And pi is a radian value, 180 is in degrees. So if we do an example here, convert 65 degrees to radians, we take the 65, multiply by pi over 180. Again, I have the units here, pi in radians, 180 in degrees. When you multiply, you can think of this as 65 over 1, multiply across. So we get 65 times pi, 65 degrees times pi in radians over the 180. We have to reduce that. This is going to be in radians. The degrees are going to cancel out. Both of these have a factor of 5. So 65 is 5 times 13, 180 is 5 times 36. Divide both by 5, they cancel out, and our reduced form is 13 pi over 36, and that's in radian measure, okay? Another example, if you want to convert degrees to radians, we have 200 degrees, convert to radians. Again, take the value, multiply by pi over 180. 200 times pi on top over 180. Now my degrees cancel out, degree over degree. We also have both of these end in 0, so we can divide both by 10, which is knocking out the 0. Reducing further, I have 20 pi over 18 left, but that still reduces. Both 20 and 18 have a factor of 2. 2 times 10 is 20, 2 times 9 is 18. Those 2's cancel. What's left? 10 pi over 9 in radians. So basically, to convert, you have a degree measure, multiply by pi over 180, and be sure to reduce, and then you get your value in radians. Okay, what about going the other way? If you have a radian value and you want to convert to degrees, you take the given value that you have in radians, and now you're going to flip what we multiplied by. You're going to multiply by 180 over pi, 180 degrees over pi radians. So whatever is given, that's what you write on the bottom. So now we're given radians, you write the radian value on the bottom, pi radians. The previous examples, we were given degrees, so the degree value goes on the bottom. Here's an example, convert pi over 5 to degrees. We set that up, pi over 5 times the 180 over pi. So you multiply numerator with numerator, pi and 180 pi. On the bottom, denominator with denominator, 5 times pi, 5 pi. The pi's cancel out. We still have to reduce the 180 over 5, and that gives us 36, so that's 36 degrees. Another example, we have pi over 12, radian value. How do we convert that to degrees? We're going to multiply by this conversion rate right here, 180 degrees over pi radians. Again, that's the original value is in radians, so that radians over radians is going to cancel. We have 180 pi over 12 times pi. Pi's cancel. We still have to reduce 180 over 12. It gives us 15 in degrees, 15 degrees. So again, quick review, you're given a value in radians, multiply by 180 over pi to get that value and make sure to reduce at the end. Okay, so another concept you guys should have seen is arc length, and we have a formula here. For a circle of radius r, a central angle theta intercepts an arc of length s given by s equals r times theta. S is the length of a circular arc, theta is the angle, which is measured in radians, and r is the radius. So we have an example here. It's nice to see this picture as well. It says a circle has a radius of 4. So here's our circle radius of 4. Find the length of the arc intercepted by the central angle of 240 degrees as shown in the figure below. Okay, arc length, what is that? It's the length, right? It's a piece of the circle. If we wanted the length of the whole circle, that's our circumference. An arc is just a piece of that circle, okay? So when you're asked for an arc length, you're finding the length for a certain section of a circle. We need to know the radius value of that circle, and then we need to know the angle, right, that we have right here that makes that arc length. The angle value needs to be in radians though, and then we just plug it into our formula. The arc length S, we just multiply the radius times theta. However, theta has to be in radians. So here, before I continue on, I need to convert the 240, which is in degrees, to radians. So we're going to use what we just previously did. We have the value 240 in degrees. I'm going to multiply by pi over 180 and reduce. When I reduce that, divide 240 by 180, I get 4/3 pi. So now I have the angle value that I need in radian mode, so I can go ahead and plug it into my formula here. S, my arc length, is going to be r, my radius, which is 4, times theta, which is now 4 pi over 3. Again, use the radian value. Multiply all that. 4 times 4 is 16, 16 pi over 3. Pay attention to how they want you to write your answer. In decimal form, we would just multiply all of this out. 16 times pi. You should have a pi on pi button on some calculators. You can just type that in. So 16 times pi over 3, and that's our value as a decimal there, okay? And then always pay attention to how to round it, maybe to 1 or 2 decimal places or more, okay? The area of a sector, so what is that? So for a circle of radius r, we have a circle here, there's the radius. The area A of a sector of the circle with central angle theta is given by this formula here. Area equals 1/2 times r squared times theta. Again, theta is the angle, but it is measured in radians, so we need a radian value. Okay, so what is an area of a sector? Well, it's not the area of the whole circle, right? That would be all of this filled in. A sector is just a piece of the circle. So we want the area of a sector, we just want the area for a certain piece of that circle. We need to know the radius of that circle, r, and we need to know that angle measure that it makes to get that sector right there, theta, okay? We have an example here. A sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees as shown in the figure below. So here we have the distance of 70 feet and it makes an angle of 120 degrees. What is the area of the fairway watered by the sprinkle? And you can see this little area is a piece of a circle. So it's a sector of the circle that we need. So we're going to stick to our formula here, 1/2 r squared times theta. Again, just like before though, theta has to be in radians, but it was given in degrees. So we first have to convert that before we plug it in. We have 120 degrees times that conversion rate, pi over 180. Reduce that, 120 over 180, divide out any common factors, and it's 2/3, reduces to 2/3 pi. That's our radian value for this angle. Now I have everything I need to plug it into the formula. So area is 1/2, the r value is 70, 70 squared, times my theta value, 2 pi over 3. Let's see, I'm going to multiply out what I can. So 70 squared is 4,900. This 2 cross reduces with this 2, so 4,900 times pi over 3. Again, pay attention to how they want you to write your final answer. We go ahead and multiply this out, 4,900 times pi, and divide that by 3. Rounded to the whole number is 5,131 square feet. So again, pay attention to how you need to round all of these, but that's what we get for this one. Okay, another important concept that you should have seen, it's going to come up a lot, is to find the values for your 6 trig functions given a triangle. So you need to know the triangle definitions of your trig function. So we have a triangle here, a right triangle. Here's our theta, and they have these 2 sides labeled. 6 and 8 are the values. What's missing is the hypotenuse value, okay? So we're going to start with our Pythagorean theorem, and we are going to find that missing value. A squared plus b squared equals c squared. Pythagorean theorem, we're going to solve for our c squared in this case. 6 and 8 are the legs of the triangle, so that's our a and b value. So plug that in, 8 for a, 6 for b. Continuing solving, 8 squared is 64 plus 36. 64 plus 36 is 100. 100 equals c squared. Take the square root of both sides. Square root of c squared is c. Square root of 100 is 10. So this gives me now the hypotenuse value, which is 10. Now I have all the values of the lengths of my triangle here. So let's review the trig function definitions here for the triangle. Okay, cosine of theta comes from the adjacent over the hypotenuse value. Sine comes from the opposite value from that theta over the hypotenuse value. Tangent is the opposite over the adjacent value, okay? The reciprocal values. Reciprocal of cosine is secant, so that we just flip the values here. Numerator and denominator get flipped, so it's hypotenuse over adjacent value. Reciprocal of sine is the cosecant, so that's hypotenuse over the opposite. And reciprocal of tangent is cotangent, it's adjacent over opposite. So now we're going to go ahead and fill in. Here's our theta. Fill in the values to get the values for our 6 trig functions, right? Okay, cosine, adjacent over hypotenuse. Here's the cosine. Adjacent, that'd be 8 over hypotenuse, which is 10. Always reduced fractions. 8 over 10 reduces to 4 over 5. So cosine of theta is 4/5. Knowing that, we can easily get secant. We just take the reciprocal or flip these numbers, and it's 5 over 4. Sine is opposite over hypotenuse, so that would be 6 over 10. Always reduce if possible, and that one does reduce to 3 over 5. Again, since cosecant is the reciprocal, we have the sine value. Now we just take its reciprocal or flip it, and we have cosecant, which is 5 over 3. Tangent is opposite over adjacent, so that's going to be 6 over 8. Reduces to 3 over 4, and you easily have cotangent now because it's 4 over 3. So another important concept to remember is, again, how to find the 6 trig values from a triangle. Keep those definitions in mind and remember how to solve the triangle here, right triangle with Pythagorean theorem. Okay, important, we also saw a bunch of trig graphs. I'm not going to get to review all of them, but we're going to do an example of sine and cosine to help you guys remember those graphs, okay? So here we have an example. We want to sketch y equals 3 times sine of 2x. Remember our basic form here, y equals a sine bx. We use a to help us find one of the values, and then we use b as well to help us find some of our values. So we're going to look at that right now. We're going to graph one period of this one. Also pay attention directions. If you need to graph more than one period, you just extend out the one period that we're going to get. Okay. So for this one, what is our a value? Number in front of sine is a, which is the 3 for this example. Number in front of x is the b, and in this example is 2. So what does that help us with. So now for the period, we take 2 pi divided by the b value. 2 pi over b in this case is 2 pi over 2. 2 over 2 reduces to 1, so we get pi. So our period here is just going to be pi. So now we take that to find our key points, the 5 key points that we need. So if you remember, once we find the period, we just divide that by 4, and that's going to help us find our 5 key points. Period here is pi. Pi divided by 4, so we get pi over 4. So our 5 key points are going to come from intervals of pi over 4. We start at 0, and we're going to add pi over 4 each time to get our next key point. So 0 plus pi over 4, pi over 4. Add another pi over 4, we have 2 pi over 4. Add another pi over 4, 3 pi over 4. And then add another pi over 4, 4 pi over 4. We're going to reduce all of these values. Pi over 4 stays, 2 pi over 4 is pi over 2, or 1/2 pi. 3 pi over 4 stays, and 4 over 4 reduces to 1, or just pi. So that is our period. And again, we used period divided by 4, pi over 4, to help us get the x coordinates of our 5 key points. So if you recall, our 5 key points for our original sine x are right here, 0, 0. For the second key point, then we go up to a. Then our third key point, we go to 0. Our fourth key point, then we go down to negative a. And our last key point, we're at 0. So these are the x values for the original sine x. But we're going to take now our original, our key points, our 5 key points, and we're going to use this to guide us, right? So our first point is still 0, 0. Our second key point has pi over 4, and our a in this case is 3. Our third key point is pi over 2, which goes with 0. Our fourth value here is 3 pi over 4 for x, which goes with negative a, so negative 3. And then our last key point, our fifth key point, is pi, which goes back with 0. So I used the key points for our basic sine x to help guide me here, and I got my 5 key points for my graph. So here's the graph. I'll show you all the points right here. We start at 0, 0, oh, and then a is 3, so we go up to 3 and down 3. We start here at 0, 0. Our next key point would be our maximum, which is pi over 4 and 3. And then we're back at 0. That's our third key point, pi over 2 and 0. Then down to our minimum at negative 3, so 3 pi over 4 and negative 3. And then back up here to pi 0. So again, this is one period of this graph right here. These are the key points I used to graph. You can continue on from here with the pattern if you wanted another period continuing on to the right, or continuing the pattern on to the left. So that's an example there, reviewing a sine graph. Okay, what if we wanted to do a translation here? We're going to do a cosine graph, but this one includes a translation, right? So the basic equations here are y equals a times sine of bx minus c, or y equals a times cosine of bx minus c. So we know we had a horizontal translation, or a shift, because of this minus c. So it could be a plus or minus value right here that you have with the x, and that's what tells you that we're shifting horizontally, okay? We're going to use this equation, bx minus c equals 0, to help us find the left endpoint, or where we would start our key points on the graph. And then the right endpoint is bx minus c equals 2 pi, and solve for x. That's going to tell us the right endpoint of the graph, or where we would end our first period for the graph, okay? So let's do this example. We're going to sketch one period of y equals cosine, parentheses 4x minus pi. We're going to go ahead and find our 5 key points without the horizontal translation, and then later we're going to adjust. So we're just going to look at the cosine of 4x first, get the 5 key points as if it was just that graph, and then later adjust for the shift here, okay? So just like previously, we get our a value, which is the number in front of cosine, which is 1. Our b value is number in front of x, which is 4. We use that to get our period, so 2 pi over b, which is 2 pi over 4, reduced 2 over 4 is 1/2 or pi over 2. So our period is pi over 2. Now we take that and divide by 4 to get our 5 key points. Pi over 2 divided by 4. Divide by 4 is the same as multiply by 1/2. So what do we get? We get pi over 8. So we're going to use pi over 8 to help us get our 5 key points. So we start at 0 and we add pi over 8 each time to get the next key point. So I add pi over 8. Another pi over 8 is 2 pi over 8, then 3 pi over 8, then 4 pi over 8. Reduce the ones that reduce. Pi over 8 stays, 2 over 8 is a 4th pi, 3 over 8 stays, and then 4 pi over 8 reduces to 1/2 or pi over 2. These are the key points that I'm going to use now to get my graph, okay? So like sine, we have cosine. However, these are the 5 key points on our original cosine. It's going to help me get the 5 key points for this graph. On our original cosine, the first key point goes with a, second key point goes with 0, then negative a, 0, and a. Again, keep in mind that these are the 5 key points for the original cosine, so those x values are from the original cosine. But I'm going to use this, plug in my 5 key points, and then help me see the output with the a and negative a or 0 values, right? So my first key point is at 0 and 0 with a, so 0, 1. My second point will start with the pi over 8 that I got here, but that's going to go then with 0. My third key point right here goes with pi over 4, but then it's negative a, negative 1. My fourth key point is going to have 3 pi over 8 and then 0. And then my last key point starts with pi over 2 and with the a value again, 1. So I got the 5 key points. Again, I have not accounted for this minus pi, which shows a horizontal shift, but I think it's easier to start this way. So we have our 5 key points. Here they are on this slide. Now we're just going to account for that shift, okay? So remember, that left endpoint where we're going to start this graph, we take the 4x minus pi, set it equal to 0. We're going to solve for x, so we add pi to both sides, 4x equals pi. Get x by itself by dividing by 4, so x is pi over 4. So if we shift pi over 4, that means that we take these original points and we're going to have to add pi over 4 to all of the x values to show that shift. Our right end point, 4x minus pi, is 2 pi. When I solve for x, I add pi first to both sides, 3 pi. Divide by 4 to get x by itself, 3 pi over 4. This means that my first period should end here at 3 pi over 4. So we'll check that, okay? So again, doing the left endpoint, solving for x, because I got pi over 4, I need to add pi over 4 to all of these x values to represent that shift, okay? That minus x right there, shift. So 0, 1, I add pi over 4 to that x coordinate, or 0. I get pi over 4 and 1. Next point, I add pi over 4 to that x coordinate, which gives me reduced 3 pi over 8 and 0. Next, I add pi over 4 to that x coordinate, pi over 4 plus pi over 4 gives me reduced pi over 2, negative 1. Again, I add pi over 4 to 3 pi over 8, add and then reduce 5 pi over 8 and 0. My last point, pi over 2, add pi over 4, and I get 3 pi over 4 and 1. So again, I started with my original 5 key points without the shift, figured that I had to add pi over 4 to each of the coordinates to compensate for that shift, got the new points that I'm going to have to graph. So these are my 5 key points with that shift. So let's look at that graph right here. So remember, cosine, it actually starts right here at the top, pi over 4 and 1. So that should be my first point. I go up to 1, I go down, negative 1. So at pi over 4 and 1, that would start my graph right there. 3 pi over 8 and 0 is the next one. Then at pi over 2, I'm down to negative 1. That's my next point. 5 pi over 8 and 0 is this point right here. And then at 3 pi over 4, I have 3 pi over 4 and 1, and that is this point. So from right here to over here, that is one period of this cosine graph, okay? And again, depending on if you need more periods, you continue with another period, that pattern, either on the right or left side of this graph, okay? Okay, another key point is solving a triangle. So I have this triangle here. What does it mean to solve a right triangle? Is to find all the values of capital A, B, and C, which are all the angle values, and all the values of lowercase a, b, and c, which are all the lengths of the sides. So we did some examples of this last week. Depending on what you're given, what values are given, you know where to go from there. So I'm going to plug in the values that I already have. I was given that a is 3, so I know that length. And then little b is 4, so that's another length. I have that one. I also have the right angle here at C, so I know that C is 90. Okay, so this is where I start. I have to plug in all the other values. I need to find the angle values A and B, and I need to find the other side length C. Okay, so based on what is given here, I'm going to start with finding C. I have A and B. Again, it's a right triangle. I'm going to use Pythagorean theorem to find my hypotenuse. So a squared plus b squared equals c squared. Plug in the a and b values that I have, 3 and 4. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. Square root of 25 and square root of c squared gives me that c equals 5. So now I have that value. Now I'm going to continue on. I have those 3 length values. Now I'm going to go ahead and find some of the angle values. So that is where my trig definitions come in. I need to use one of these trig formulas to help me find the angle values, okay? I'm going to start with sine, and I'm going to start with A. So if I want to find the angle A right here, okay, I'm going to use one of my trig functions. I'm going to use sine. So I know that sine is opposite over hypotenuse, which would mean that that's 3 over 5. So I plug the values in that I know, 3 and 5. Now I want to get the A value. I want to solve for that. So I'm going to take the inverse sine or the arc sine of both sides. I'm trying to cancel the sine and just get the A value by itself. So I do the inverse of sine or arc sine of both sides. Arc sine and sine are going to cancel here and just leave me with the A. And then I need to find the arc sine of 3 over 5. So you would take out your calculators, do that, and we should get that the value is 36.87. Again, pay attention to how they want you to round, but to 2 decimal places, that's 36.87, and that is our A value. So what's left? I just need to find B. I actually can do the same thing again, but using the B instead, right, for theta. Or now that I have all of my other angle values, I have 2 angle values, I know that the 3 interior angles of a triangle add up to 180. So now that I have 2 of those, I can just go ahead and subtract them from 180 to give me the third one. So again, the 3 angles, interior angles of a triangle add up to 180. So if I have 2 of them, I subtract and it'll give me that third value. So I'm missing the B. If I do 180 minus the A value minus the C value, it gives me the B value. So what do I get? I get 53.13 degrees for this one when I round, because remember this value right here we rounded, and that is the rest of it. So again, just a quick review, solving a right triangle means to find all the lengths and all the angle measures for the triangle. Depending on what's given, that's how you know where to go, but we use Pythagorean theorem to find our missing side length, and then we use some of our trig function values to find the angle and go from there. Okay, so then you have some word problems that you saw. Some of them have a picture, but I like this one because it doesn't have a picture, and you need to practice maybe kind of drawing your own picture that goes with some of these, right? So let's see here. A ladder that is 20 feet long leans against the side of a house. The angle of elevation of the ladder is 80 degrees. Find the height from the top of the ladder to the ground. Okay, let's do our best to draw this one. Ladder leans along the side of a house. So if this is my house, if this is the side of the house, this is my ladder that leans along it, right? The ladder is 20 feet long, so we have that value right there. The angle of elevation, so from the ground up to the ladder, the angle of elevation is 80. So what does that mean? It means that this angle right here is now 80 degrees. So they want us to find the height from the top of the ladder up here down to the ground. So we're finding this height right here. I'm going to label that as that's our variable. So again, some of these word problems you see already have it all drawn out, but sometimes you're going to have to know what everything is and do the graph yourself, which is why I like this example here. Okay, we have another right triangle. We're going to set this one up so that we can solve for that x value. Okay, what is given here? We are given the hypotenuse and we are given an angle. So we're going to use a trig function that includes these to help us solve. Okay, here are the trig function values for the right triangle. So I'm going to use sine because sine includes the opposite and the hypotenuse for this angle, which are the two values that we're working with here. I need to solve for one and I have the other one, but I can plug values in here, right? So theta is 80. The opposite is the x that I'm solving for, and the hypotenuse length is 20. So I have this set up. I need to find the x value. So I'm going to multiply by 20 on both sides to get x by itself. So x is going to be 20 times sine of 80 degrees. You would take out your calculator, plug that in, and we should get 19.696. Again, pay attention to how they would like you to round. This one I did to 3 decimal places. Sometimes you might need to round to 1 or 2 decimal places, so keep that in mind. But that would be for this one. If we did round to 1 decimal place, it'd be 19.7 as an example. Okay, also evaluating trig functions from a point. Okay, so we have this one. Let -3, 4 be a point on the terminal side of theta. Find the sine, cosine, and tangent. Okay, so here's the graph. Here's the point, -3, 4 right there. And then if we draw that length right here from the origin here, that we call our R value, or that R length, right? So we want to find sine, cosine, and tangent. One way to do that, first know the quadrant that we're in, and we're going to first find R. So we are in quadrant 2. We have our trig function values in quadrant 2. But first, let's start by finding R. R is the distance, comes from the distance formula. So from here, the origin, up to that point, we can look at that as just finding the distance. We have the x and y values. So how do we find R? It's the square root of x squared plus y squared. Again, here's my point. So the x is -3, the first coordinate. The y is 4, the second coordinate. So I can just plug in the x and y values, and I'm going to solve for R. X is -3, so I'm going to get -3 squared. Y is 4 plus 4 squared. Solving, -3 squared is 9, 4 squared is 16. Adding those up, square root of 25, R is 5. So I have that R value, okay? Now, we can also look at this, because I have formulas and I can just plug those in, but I also like to look at this as a triangle. So whenever you have something like this, we can look at that as a triangle. So you would just take from that point, draw a line down to the x-axis. Here we're in quadrant 2, so we draw it down to the x-axis. If we were in another quadrant, maybe quadrant 3, we had a point over here, we would draw a line up to the x-axis. And then we can look at that triangle that we made. So here I'm looking at this triangle that we made, and it's the same type of problem that we've done before using our trig definitions. Now, this is the original theta, but when I have my triangle, I can use this corresponding angle as my theta, so I call that theta prime. So what are my values, or my looking at the length? So I put this as x is -3. I know we don't have negative lengths, but just to show you where that comes from, because x was -3, so we went out 3, so we can look at that right there. And then this represents the y. Y is 4, so we can look at that value right there. So now we just need to find our sine, cosine, and tangent. We have a triangle here with this theta inside, and we can look at those same trig definitions with theta. You can also look at those in terms of x, y, and r as well. So again, I just like to go over the triangle because it just kind of helps me see it and see this problem just like all the other ones we've been doing with our trig definitions for the triangle. But you also have these other formulas we can use. So in this case, with a point, sine is y over r. So we can just take the y value and the r value. But let me show you how that works with the triangle. So sine of theta, if I'm taking this theta, remember, sine is just opposite over hypotenuse, so yeah, that's why it is y over r. Cosine is x over r, and let's look at that. If this is my theta, cosine is the adjacent, the one next to it, which is the x over the r, and tangent is opposite over adjacent, so that's how we get the y over the x. So I just like seeing that correlation. Again, we can just plug in the values. Once we found r, we can just plug in the x, y, and r values to get these trig function values. But again, I wanted to show you just how it's a triangle and you find the side lengths and you know the values. So let's go ahead and plug this in. Y over r, which is 4 over 5. X over r, negative 3 over 5. And then tangent is negative 4 over 3. Okay, so that would be another review there for that problem. And what else? Let's see, we have another word problem. The sun is 25 degrees above the horizon. Find the length of a shadow cast by a building that is 100 feet tall. Now this one does give you a figure, so that's nice. We can see what everything is here. So here is the 25 degrees where the sun is above the horizon. Here's the building that is 100 feet tall, and we want the length of the shadow, okay, that is cast by the building. So here's the building, and again, this is the shadow, and we have the angle of 25. Okay, so this is the length that we're looking for, okay? We have an angle, we have the side opposite to it, and what are we looking? We're looking for the side adjacent to that angle. Okay, that's our x. So again, we look at our trig function values. Hopefully everybody is familiar with those for sure. Let's set up our triangle here. We're going to go ahead and use tangent because those are the lengths that we're going to be using. We have the opposite value. We need to solve for the adjacent value, which is x, but I can plug those in appropriately. So what's my theta? My angle is 25. Opposite is 100, and I need to solve for the x. There's my variable, okay? So solving this, I can cross multiply or multiply everything by x and simplify. So either way, we need to get x by itself. So it ends up with 100 divided by that tangent of 25. Taking that into your calculator, we get x is 214.45. Again, as always, pay attention to the directions and to see how they want you to round. This one here is to 2 decimal places, so 214.45 once we plug all of that in. Okay, 214.45. Okay, let's do one more example here. A guy wire runs from the ground to a cell tower. The wire is attached to the cell tower 150 feet above the ground. The angle formed between the wire and the ground is 45 degrees. Okay, we have another example here, and it does come with the figure similar to what we were doing before. A, how long is the wire, which is this value right here, which represents the hypotenuse of this triangle. B, how far from the base of the tower is the guy wire anchored to the ground? So from the base of the tower here, over here, that's the adjacent in relation to that angle right there. Okay, so doing our values again, we set this one up. Sine theta, we're going to use opposite over hypotenuse, which is going to be 150 over hypotenuse, which is what we're solving for. To get hypotenuse by itself, we end up with 150 over sine of 45. Take your calculators, plug that in appropriately. We should get 219.9. And that would be the length of the wire. And then solving for the next one, I'm going to use tangent. I'm going to use the 150 over that adjacent value. It's tangent of 43 this time. Plugging everything in and solving. If I multiply by adjacent, then solve for that, divide by tangent. Take that into your calculator, plug that in. We should get 160.9 for that value. All right, so I'm going to go ahead and stop there and ask you guys if you have any questions. Oops.
Well, thank you, Ms. Camarillo, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on the YouTube playlist. Today's session will also be available on the playlist later on today. Also linked is a short survey to help us improve our TVE sessions, so please take time to fill out that survey. Before you leave, I want to share the TVE sessions that we will have next. We'll be back next week with Happy Math Hour, in which Math 1332 will cover our next week, our conditional and related statements, symbolic arguments, and the Euler diagrams. Math 2412, verifying the trigonometry identities and implementing trigonometric formulas. Today at 1, the student success topic will be EPCC distance learning. And thank you all for coming in today. We hope you have a lovely weekend. If you have any questions, feel free to use the chat box or the mic.